You think the speed of light is just a number. 299,792,458 meters per second. Fast, very fast. It's the fastest thing there is. But have you ever stopped to ask yourself, why? Why is there a limit at all? Why isn't it infinite? And why, in the name of common sense, can you not go faster? Most people just shrug. They say Einstein said so, or it's the cosmic speed limit. But that's not an answer. That's just repeating the rule book. That's just giving a name to something you don't understand. When you actually dig into why nothing can go faster than light, when you strip away the equations and look at the machinery of the universe, you find something absolutely terrifying. You find out that the speed of light isn't about light at all. It's about the structure of reality. It's about the geometry of the stage we are all dancing on. And once you see it, you can never unsee it. Let's back up. We have to start with something simple. Something so obvious you probably stopped noticing it when you were 2 years old. Things fall. You hold a rock, you let go, it goes down. Galileo measured this hundreds of years ago. He found that in the first second, a thing falls 16 feet. Doesn't matter if it's a rock or a cannonball. 16 feet in 1 second. That is a fact. It's a measurement. Now look at the moon. The moon is up there, hanging in the sky. It is not falling down. It is going around. It is orbiting. And you might think, well, obviously the moon is different. The rock falls. The moon orbits. But this is where Isaac Newton came in and did something spectacular. He had this imagination, you see. He looked at the moon and he asked a question that nobody else was asking. He asked, is the moon falling? Think about it. If the moon were just sitting there, stopped dead in space, gravity would grab it and pull it straight down into the earth. Crash. But the moon isn't stopped. It has a sideways velocity. It's moving sideways very, very fast. So gravity pulls it down, but the moon moves sideways. It falls, but because it's moving sideways, the surface of the earth curves away underneath it. The moon falls towards the earth, but it keeps missing. That is what an orbit is. It is a continuous, eternal fall, where you are going so fast sideways that you never hit the ground. Now, Newton, being a clever fellow, he wanted to check this. He knew the moon was 60 times further away from the center of the earth than we are. We are 4,000 miles from the center. The moon is 240,000 miles away. That's a ratio of 60. Newton had a hunch. He thought maybe gravity gets weaker as you get further away. Maybe it spreads out like butter on toast. If you spread butter on a piece of toast that is twice as big, the butter is 1/4 as thick. It's an inverse square law, the square the distance. So if the moon is 60 times further away, gravity should be 60 squared times weaker. What is 60 squared? It's 3,600. Newton said, if I am right, the pull on the moon should be 3,600 times weaker than the pull on my apple. On Earth, the apple falls 16 feet in 1 second. So the moon should fall 16 feet divided by 3,600. Do the arithmetic. 16 feet divided by 3,600 is about 1/20th of an inch. So Newton calculates, in 1 second, does the moon fall 1/20th of an inch towards the earth. He looks at the orbit, he looks at the timing, he does the geometry, and it matches. It matches exactly. This is the moment the universe changed. This is the moment we realized that the laws of nature down here are the same as the laws of nature up there. It was the first time we understood that the heavens were not some magical realm made of different stuff. It's all the same stuff. It's all obeying the same rules. Now, before we go further into the madness of light speed, I want you to do something for me. If you think it is absolutely beautiful that the fall of an apple and the orbit of the moon are actually the same phenomenon, I want you to hit the like button on this audio. Just tap it. It tells the algorithm that we care about understanding the universe, not just looking at it. And if you've ever wondered about this stuff yourself, leave a comment saying gravity. Okay, let's keep going. So Newton has this law, the law of gravitation, and it is powerful. It explains everything. It explains why the planets move in ellipses. Kepler had seen the ellipses, but Newton explained why. He got that for free. It explained the tides. People used to think the earth was breathing, or the water was being pulled by magnetic spirits. Newton said, no, it's the moon. The moon pulls on the earth. But wait, if the moon pulls the water, why are there two tides? There is a bulge of water on the side facing the moon, sure. But there is also a bulge on the exact opposite side, facing away from the moon. 2 high tides a day. Why? It's the same law. Gravity gets weaker with distance. The water on the near side is closer to the moon than the center of the earth is, so it gets pulled more. It pulls away from the earth. The earth is closer to the moon than the water on the far side is, so the earth gets pulled more than the far water. The earth is pulled away from the water. So you get a bulge on both sides. It's a differential force. It's elegant. It's simple. Everything was falling into place. We understood the solar system. We could predict where the planets would be. We felt very smart. But then, as we started measuring things more carefully, we found a crack in the armor, a tiny little crack. Pause. It started with Jupiter. Jupiter has moons. Galileo discovered them. And because we knew Newton's laws, we could predict exactly when those moons should disappear behind Jupiter, an eclipse. We had a schedule. An astronomer named Romer was watching these moons. He was a careful guy, and he noticed something funny. Surprised. When the Earth was close to Jupiter in our orbit, the moons were on time. They followed the schedule. But when the Earth was on the other side of the solar system, far away from Jupiter, the moons were late. They were 8 minutes late. Now, 8 minutes is a huge amount of time in astronomy. It's an eternity. Most people would have said, Newton is wrong, or Jupiter is acting weird. But Romer had confidence in the law. He thought, the law works. The moons are moving correctly. So why do they look late? And he realized, it's not the moons, it's the news. The news of the eclipse, the light carrying that image, has to travel to us. When we are further away, the light has to travel an extra distance. It takes time for the light to get here. This was a shock. Before this, most people thought light was instantaneous. You open your eyes, you see the star, instant. But Romer showed that light has a speed. It takes as time to travel. He calculated that light takes about 8 minutes to cross the orbit of the Earth. He measured the speed of light not by building a machine, but by looking at the delay in the schedule of Jupiter's moons. That is the power of a good theory. When the observation doesn't fit, it suggests a new phenomenon. So now we have a speed, 299,792,458 meters per second. We call it c dot. And for a long time we thought, okay, that's just how fast light goes. Sound has a speed, light has a speed, no big deal, excited, but then came the experiments. And this is where the universe starts to look absolutely crazy. You see, usually speeds add up. If I am on a train going 50 miles an hour, and I throw a baseball forward at 50 miles an hour, the guy standing on the ground sees the baseball going 100 miles an hour. 50 plus 50. Simple. Common sense. So we thought light must be the same. If I am on a rocket ship going half the speed of light, and I shine a flashlight forward, the light should go at the speed of light plus the speed of the rocket. Right? Wrong. When we measured it, we found something impossible. It doesn't matter how fast you are moving. It doesn't matter if you are standing still, or on a train, or on a rocket moving at 99% of the speed of light. If you measure the speed of that beam of light, it is always exactly the same number. The speed of light does not add. Imagine you are running down the street at 10 miles an hour. You throw a ball. The ball goes faster because you are running. Now imagine you are running down the street and you turn on a flashlight. The light does not go faster because as you are running, it leaves you at the speed of light and it passes the guy on the sidewalk at the speed of light. This breaks your brain. How can the light be moving at the same speed relative to me, who is running, and relative to you, who is standing still? That shouldn't be possible. If I am chasing the light, I should see it moving slower, right? I should be catching up to it, but I can't catch up. It always recedes from me at the exact same speed. Pause. This was the crisis. And this is where Albert Einstein stepped in and said something so radical, so counterintuitive, that people still struggle with it today. Einstein said, if the speed of light is constant, then everything else must change. If the speed is fixed, then distance and time must be flexible. Think about what speed is. Speed is distance divided by time. Miles per hour, meters per second. If the answer has to stay the same, but you are moving differently, then the meters and the seconds have to change to compensate. This is relativity. When you move fast, time slows down for you. Literally, your clock ticks slower compared to a guy standing still. And space contracts. The distance in front of you actually gets shorter. The universe squashes space and stretches time, specifically to ensure that the light beam always measures at exactly the same speed. It's like a conspiracy of nature. To catch the light, the universe slows down your time and shrinks your ruler so that when you measure the light, it's still zooming away from you at exactly CQC dollars. So, the speed of light isn't just a speed. It is a conversion factor. It is the exchange rate between space and time. And this leads us to the ultimate question. Curious, why can't we go faster? If you try to push a spaceship to the speed of light, you add energy. You burn fuel. You push harder. You go faster. But as you get closer to that limit, strange things happen. The faster you go, the more energy you have. But Einstein told us that energy and mass are the same thing. $E equals mc squared, $. So as you add energy to go faster, you are effectively adding mass or inertia to the ship. It becomes harder to push. You push more, you get heavier. You push more, you get heavier. It's a diminishing return. As you approach the speed of light, your inertia approaches infinity. To actually reach the speed of light, you would need infinite energy. And there isn't infinite energy in the universe. So you can never get there. You can get the 99%. You can get the 99.9999%. But you can never reach the limit. The only things that can travel at the speed of light are things that have no mass. Photons. If you have no mass, You must travel at the speed of light. You don't have a choice. You can't slow down. But here is the deepest part, the part that keeps me up at night. We call it the speed of light, but that's a bad name. It's really the speed of causality. It is the maximum speed that two things in the universe can talk to each other. If the sun disappeared right now, vanished, we wouldn't know for 8 minutes. The Earth would keep orbiting nothing for 8 minutes. We would still see the sun in the sky for 8 minutes. Gravity travels at the speed of light. Information travels at the speed of light. Curious. Why? Because space and time are fused together. We live in space-time. Imagine you are in a car. You can drive north, you can drive east, or you can drive northeast. If you drive northeast, you are sharing your speed between the north direction and the east direction. You aren't going as fast to the north as you would be if you went straight north. Now apply that to space-time. You are always moving through space-time. Even when you are sitting in your chair perfectly still, you are moving. You are moving through time. You are traveling into the future at the speed of 1 second per second. You are hurtling through the time dimension. Now, if you stand up and start walking, you are moving through space. But here's the rule. You have a constant speed through space-time. If you divert some of your speed to move through space, you have to subtract it from your movement through time. This is why time slows down when you move fast. You are turning your vehicle. You are borrowing speed from the time dimension to use in the space dimension. If you could move through space at the speed of light, you would have used up all your motion. You would have zero motion left for time. Time would stop. This is why you can't go faster than light, because you can't move slower than stopped in time. You can't have negative time. You can't arrive before you left. Whispers. From the perspective of a photon of light, time does not exist. It is emitted from a star 1 billion years ago, and it hits your eye today. For us, 1 billion years passed. For the photon, zero time, instant. Birth and death are the same moment. The universe has a structure. It has a geometry. And that geometry puts a limit on how fast cause and effect can happen. We have tested this. We measure it every day. We have particle accelerators that push protons to 99.99999% of the speed of light. We pump more and more energy in, and they just won't go faster. They just get heavier. We have GPS satellites. They are moving fast in orbit. Their clocks tick at a different rate than the clocks on our phones. If we didn't program Einstein's equations into the GPS satellites to correct for this, the map on your phone would be off by miles within a single day. This isn't just theory, this is engine. Airing. This is how the world works. So to summarize this avalanche of ideas, exhales, it started with Galileo watching things fall. It went to Newton realizing the moon is falling, but missing the Earth. Then to Romer realizing that because the moons of Jupiter were late, light must have a speed. Then to the discovery that this speed is constant no matter what. And finally to Einstein, who showed us that because the speed is constant, space and time are not. They are flexible. They are the same thing. The speed of light is the limit because it represents the fundamental relationship between space and time. It is the conversion rate. It is the speed of now. It's not a barrier put there by the police. It's the edge of the map. It's the way the fabric is woven, excited. And isn't that just fantastic? Isn't it better to know that than to just be told it's the limit? We are these tiny little creatures living on a rock, orbiting a star, in a galaxy of billions of stars. And yet, by thinking, by measuring, by watching the moons and the tides, and the falling apples. We have figured out the rules of the game. We know the structure of the stage we are standing on. That is the beauty of physics. It doesn't just tell you what happens, it tells you how. And if you look closely enough, it tells you why. Keep asking questions. Keep wondering why, because the answer is always stranger and more beautiful than you can imagine.